Howdy, howdy. This is Mr. Potter. We're going to be talking about a new concept here. The idea is that we've been trying to estimate the area under curves, and we've been using Riemann sums as the tool to do that. But what I want to do is I want to try and get away from this idea of just estimating the area under the curve and actually calculating the area under the curve, getting a more precise answer. Now, Riemann sums really are the tool that we're using here. But keep in mind that what we're doing is when we're looking at a Riemann sum, whether it's an left Riemann sum or a right Riemann sum, we're always taking f at some particular x coordinate times delta x. So this is our height of our rectangle. This is the base of our rectangle. And we're adding this to another height times base. And we're adding that to another height times base. So what I'm really doing is I'm adding a whole bunch of these. Now in our examples, we've kept it to 3 or 4 or 6 or something like that. But in reality, I could have 10 of these. I could have 50 of these. I could have 100 of these. And because this delta x getting smaller gives me more rectangles, the rectangles can better conform to my graphs. So it's going to give me a better area approximation. And so what we're noticing here is that the more rectangles I have, the better of an approximation it is. Now what we're really doing here is we're really taking the summation of f at some x of k times delta x as k goes from 0 to some number n. So this is really the sum of n rectangles. So the idea here is that if the more rectangles I have, the better of a fit I have. Then what happens if I take the limit as n goes to infinity? Now, back in chapter 2, we talked about limits as n went to infinity, and we noticed that there were behaviors that we could deduce from this. And chapter 3, we had a lot of limits where our terms were going to infinity. We're basically taking an infinite number of secant lines to get this tangent line. So if I take the limit of this summation as k goes from 0 to n of f of x of k delta x, one of the things I want to recall is that when we let this limit of the changes, if the number of rectangles is going to infinity, that means that this delta x is really headed towards 0. It's kind of like the h that was headed towards 0 in the definition of our derivative. And we notice that the delta x in our differential, in our derivative, in our slope, became dx. This idea of moving from the Greek letter to the Latin letter. And so one of Leibniz's ideas, well, if I'm doing that to this delta, why can't I do it to this sigma? And so that's what he does. Now, of course, this is the 17th century, so the s is actually these long s's, like you see in some really old documents. And so what I'm really doing is I'm doing this integral symbol. This integral symbol that we're used to seeing, that we discussed a whole lot back in chapter 6, actually comes from this idea of transforming a sum of finite rectangles into a limit of letting those number of rectangles go to infinity. And so what's happening is, instead of talking about the kth interval, or the 0th interval, the first interval, all the way up to the nth interval, I actually talk about this going from some x in point A to some x in point B. Now, mathematicians are lazy, so we'll often write this just as the integral from A to B of f of x dx. And this gives us something which we call a definite integral. And so when I talk about a definite integral, there's a definition that we use. Whenever I talk about the integral from x equals a to x equals b of my function f of x dx, this is defined as the area lying below f of x between x equals a and x equals b. In other words, whatever function I have, the area that lies between x equals a and x equals b, this is the integral from a to b of my function f of x dx. So, in other words, this notation is really another notation for the area. But this is not an approximation. This is an exact area. So in other words, I'm finding the exact area under this curve. I want to start by talking about it from a purely geometric sense. The idea is that I'm going to be using geometric formulas to determine these definite integrals. So I'm going to start by evaluating the integral from 1 to 4 of 3 dx. So what this is really saying is that I have a constant function, y equals 3. And I want to know what the area of the under the curve between x equals 1 and x equals 4. Well, this shape is a rectangle. And I know that the area of a rectangle is equal to base times height. So this is really, my height is 3, and my base could be determined as 4 minus 1. So this is really 3 times 4 minus 1, or 9. So the area that lies under this curve is 9, and we're finding it using geometry. So I want to go through a few more examples of this. Let's say that I want to determine the definite integral from x equals 1 to x equals 5 of the function x dx. So I know the graph of y equals x is a diagonal line with a slope of 1. And I know that when x is 1, the point on my curve is the point 1, 1. And when x equals 5, the point on my curve is the point 5, 5. And so I'm looking for this area here. And this is a trapezoid. I know the formula for the area of a trapezoid is 1/2 base 1 plus base 2 times the height. My height is the distance between these bases. So my height is really 5 minus 1. And base 1 and base 2 are 5 and 1 respectively. So I've got 1 plus 5 for this base 1 plus base 2. And so my area ends up being 1/2 times 6 times 4, which gives me an area of 12. So the area of this trapezoid is 12. That means that this definite integral evaluates to 12, just like this top definite integral evaluates to 9. And I know some of y'all that have seen a little bit of calculus before are thinking these are rather obvious entries. But there are other ones that we can't do using our standard techniques, but we can do using geometry, such as this function, which we've been dealing with. We've been only dealing with the approximations of 16 minus x squared times delta x. But now we can find the exact value. And we can find the exact value because we're talking about a quarter of a circle. This is a quarter of a circle with radius 4. And so our area is going to be 1/4 of pi r squared. We're just using a pure geometric way of looking at this. So this is going to be 1/4 of pi times 4 squared, or 16 pi squared, 16 pi over 4, which is just 4 pi. So the area under this curve is 4 pi, and that means that this definite integral evaluates to 4 pi. Now this is about 12.5, and we've used approximations in our previous lessons to deal with this expression. We've got values between 11.5 and 13.5. So this 12 pi this 12.5, which lies right in the middle, this is our exact answer. I want to do one more example of this just using geometry, and that's to find the definite integral between x equals negative 2 and x equals 3 of the absolute value of x. Now I know what the absolute value curve looks like. Normally my curve looks like a V, but I'm restricting the domain from negative 2 to 3. And so when I'm talking about the area that lies under the curve, I'm talking about two triangles. So my area is going to be 1/2 base times the height is 2 plus 1/2 the base times the height of this triangle is 3. So this is really 2 plus 9/2, or 13/2. And so I know the area under this curve here and here, that area is 13/2. So I can talk about this from a purely geometric standpoint, using the formulas that we've learned in our geometry class. The formulas for areas of rectangles or trapezoids or circles or triangles. But there's another way that we could do this, and it's just by taking a look at the transformations that we learned back in Algebra 1. So let's say that I'm telling you for sure that the integral, the definite integral from 0 to 1 of x to the fourth dx is 1/5. And this is something that I can find using a calculator. This is something I could find using a table in a book. But this is the answer from 0 to 1. So my question is, what if I was to do a transformation on this function? In other words, what if I was to ask you to evaluate the definite integral from x equals 0 to x equals 1 of 1 plus x to the fourth dx? What does this do to my graph? Well, I know that my original graph looks like a flattened parabola. In other words, it starts off very shallow, it goes very steep. So this area here is 1/5. But if I take a look at what I've done here, I've taken this graph and I've essentially translated it up 1 unit. And so I've got this part here, which is 1/5. But I know that this here is a rectangle with the base of 1 and a height of 1. It's really a square. And so the area for this shape is the 1/5 that we had plus 1 times 1. So my definite integral evaluates to 6/5. Now I could do something else with this, because this is an even function. I could consider the situation where I'm evaluating from x equals negative 1 to x equals 1 of x to the fourth dx. Because what I'm doing now is I'm looking at this from a standpoint, I not only want from 0 to 1, but I also want this from negative 1 to 0. In other words, I want this total area. Well, I know that this part is 1/5. That was given to us. But this is an even function. And so this interval must also be 1/5. And so the total area under the curve from x equals negative 1 to x equals 1 would be 2/5. And there's another way that I can look at this. I know what the graph of x to the fourth look like, and so I also know what the graph of x to the 1/4 looks like. I know that graph is going to be very similar to just reflected across the line y equals x. So if I'm trying to evaluate the area under the curve from x equals 0 to x equals 1 of x to the 1/4 dx, I'm not looking at this area. I'm actually looking at this area here, from x equals 0 to x equals 1. Well, this is a square that has an area of 1 minus this area that's unshaded, which I know from my given information is 1/5. And so the definite integral will evaluate to 4/5. So if I know one piece of information, I can apply what I've learned in my algebra classes to transform a function to get this information where I can talk about translations, where I can talk about reflections, where I can talk about another type of reflection and subtraction of area. So I have these powers to work with these definite integrals. Definite integrals are a number. They determine the area that lies under the curve, between the curve f of x and the line y equals 0. And so we're going to continue talking about these definite integrals. And later on in this chapter, we'll talk about why this symbol looks so familiar. So, thank you for watching. This is Mr. Potter. Have a great day.